In the third example of applying the slope deflection method, we have the same structure and loading and support movement as we did in example 2, but the big difference is that we've removed the fixed end out here at the right side. That changes everything that's going to happen quite a lot. We no longer know, in addition to not knowing the rotations at B and C, we don't know what happens at D, nor do we know the chord rotation at D. Right, and so that means that we have 1, 2, 3, and 4 kinematic degrees of freedom. Now, the other two chord rotations for A, B, and BC are still not zero, but they are known or can be calculated based upon what we did last time and what you see down here below. It's this addition now of how we got a chord rotation out here that we could refer to in terms of the translational displacement D, or we could leave it in terms of psi, either way that we'd like to proceed. All right, so we have a total of 4 unknown member end displacements. Now, for the most part, this will flow in the same kind of way as before. You go to the joints where the degrees of freedom are at, and for those rotational ones at B, C, and D, it's relatively straightforward. For instance, at B, then we'll have those two member end moments MBA and MBC, and the sum of those will have to be equal to 0. Same thing at C. We'll have MCB and MCD, and the sum of those has to be equal to 0. Likewise, at D, we only have one, MDC. If you wanted to, of course, you could write that the sum of those is also equal to 0. There's, of course, only one of those. Now, remember that this is not trivial. It might seem like that in the old equilibrium-based days, but in the stiffness days, that's not trivial at all. That's very important, because remember that MDC is going to be equal to 4ek theta d plus 2ek theta c minus 6ek psi cd, and plus a fixed end moment. And because of that, then you get a pretty important equation. In fact, so important, let's go ahead and write that out again. That since we only have one moment here, that's going to be MDC equals 4ek for that member times theta d plus, that's the near one, and then theta c minus 6ek for that member times psi cd plus the fixed end moment dc. Right, now, don't get confused here. I know that we don't really have a fixed end out here, but in this methodology we pretend that we do. There are ways to simplify these things in a variety of different ways. We're going to talk in the next little bit about a slightly different approach to this, but a way that simplifies things down a little bit. But yeah, wow, I mean, this is an equation that has 1, 2, 3 of our kinematic degrees of freedom in it, and that's a pretty crucial one to have. But still, we only have 1, 2, 3 equations, and we have 4 unknowns. We need one more. And when you have this unknown amount of sway, what you got to do is here's the one spot where you have to be creative, and that is to figure out how to look at the member such that you'll get another equilibrium equation that involves a member end moment. So, for instance, in this case, because we have this cantilever up here, we can come right to the right of that support, and we can then put our loads on, and that is what, 100 kilonewtons per meter, and it's 5 meters long. And note what happens here. We'll have a shear force at the end, that's VCD. That's going to be easy one. That's going to be equal to 500 kilonewtons. and we're going to have a moment. Now make sure you use the positive sign convention here. There's your MCD, not DC, because we know that MDC is actually 0, so we don't have to show that one at all. It's not going to really add anything of usefulness to us. We're just doing straight static equilibrium. And once again, note that becomes kind of important, because equilibrium will tell us that MCD has to be equal to minus of, well, this 100 times the 5 times 2.5, which will be, I think, 1250. Let's check it. 500 times 2.5, sure enough, that's 1250. And based upon the equilibrium we have here, that of course will be negative. And just as before, that's so important, because that gives us this fourth equation, because MCD is equal to 2ek CD theta D plus, I'm swapping the order of things here, plus 4ek CD theta C, just swapping the order that we had up here and changing the coefficients. Not changing the order, sorry. I'm keeping the order, but I'm changing the coefficients to reflect near and far ends. Minus 6ek CD psi CD, and then plus the fixed end moment CD. Right? And again, this is a non-zero value. It's the minus WL squared over 12. Just like this one would be the positive WL squared over 12. Doesn't match the physical conditions of the structure, but we've accommodated it in the whole system. Seems a little weird, and it is kind of strange, but it does give us exactly the information about the rotation at D and the chord rotation at D for the member. But what if we didn't care? What if all we wanted were the two support forces B and C, so that we could go do the rest of the equilibrium and get the rest of the reactions, right? And so that's where you could take this idea of just chopping off the cantilever, and we can reduce this problem down right away. Make sure that you put the statically equivalent set of forces on. And now, when you look at this system, we only have 2 kinematic degrees of freedom that we are not knowing. Right? We got the rotations at B and C. We still have the support movement. Okay, that's all right. But now when you go play with the free body diagram of the joint, so we can get our equilibrium equation, now what you're going to do is you're going to have, of course, a shear and a reaction and the 500 that's coming in from there, but we don't care about that part. That's not what's the crucial part. Instead, what matters is that we've got that 1250 being applied there, and on the joint we would have it counterclockwise. That would be MCB, and our equilibrium equation then would be, well, MCB equals 1250. So that means that we have, at that part, then 4ek BC times theta C plus 2ek BC times theta B minus 6ek BC times psi BC plus the fixed end moment CB, and that's going to be equal to a positive 1250, and that would be the equilibrium equation you get out of C. This is the first time we've seen the moment being applied right at the joint, and that's how you just put it in. Instead of being the sum of all those moments equals 0, instead it has to be equal to that applied moment. Right? And of course B is no different than it was before. That one's still going to be that MBA plus MBC will equal 0. So notice here, at the joints, we get that generality that will sum at the joints all the moments that frame into that joint. And it'll be either equal to 0 or the applied moment. Keeping track of the sign as you go.